level inverters. So what are the content that we are going to cover? So we'll start with a basic introduction to microgrid. So which I definitely know that all the presenters so far whoever has taken the session would have divided into. Right? So we'll try to have a very brief touch up on microgrids. Then what does the typical microgrid architecture look like? Then I'll try to show some of the simulation studies, and then we'll get into the multi-level inverters. A brief introduction again. Then I'll try to showcase some of the work that we are trying to do or that we have already done in this particular area, and then I'll conclude the presentation. So that is what the overall presentation would look like. So let us start. So microgrids. So as the name itself says, it is a cellular power architecture. So what is the basic definition? So that is what it is. So basically, microgrid refers to the electricity sources like solar photovoltaics, or it could be PV, or it could be battery energy storage systems, right? And it is a localized group. So that is what it makes it to differentiate from a regular power grid that we have, because in a regular power grid we have a generation happening somewhere very far away from the consumer end. So from the consumption point, the generation is very far. Whereas a microgrid generally refers to a localized generation of electrical energy. And also we have loads that are part of our microgrid, and they're connected. It could be connected to a centralized grid, but can also disconnect, and it can function autonomously in the islanding mode. Okay. So that is a simple definition, a localized group of sources and loads that might be connected to a centralized grid, or it could function autonomously on its own in islanding mode. So what are the typical components of a microgrid? So on the generation side, we can have a hybrid mix. Then as a hybrid mix, we can have a mix of like wind, solar, and everything, whereas PV is typically considered as a base load for of microgrid. Or when I say load, that means that is what it supplies. So PV can be considered as a source that takes care of the base load of a microgrid. And we can have a storage of a battery energy storage system, or we can have a flywheel for the inertia management. That is different. Then in addition, we should have a controller whose main function is to make sure that the energy management happens. So what exactly do we mean by energy management is that these sources, or like the PV, wind, they have the energy they generate is a controllable energy, right? So they are not, there would be uncertainty. Definitely there is uncertainty in their generation. So we don't know when the PV power is going to peak or when it is going to go down. So we need to have some management system that will not let the load to see this kind of fluctuation, right? So that is the main job of a energy management system. In addition, so how do we do that? So energy management, basically it is going to take care, or it is going to make sure that if there is any excess energy that is available, it will be dumped onto the batteries so that it will get stored. And whenever there is a deficit, that will be retrieved back. So that is the main job of a central controller or energy management system, where we can have nowadays we have AML for demand response. So demand response is possible in a microgrid, wherein we, depending on the load availability and depending on the source availability, we can schedule the load, and also seamless resynchronization. So this resynchronization is required whenever the our microgrid gets into island, and it has to be seamlessly connected back to the grid. So why is it important for Indian microgrid? Because we are projected to reach a $15.3 billion by 2033, right? So current drivers are, there are many schemes that the government of India has. PM Kusum scheme is one where then we also have Urja scheme where there is several solars that are being incentivized for the deployment, right? So that in that regard, solar PV has a very large role to play in the coming future, which has already started. Okay. Okay. Now, typical microgrid. So, what and all it has? What are the major components that we have in a typical microgrid? So you can see here we could have a PV array, and we could have variety of sources like fuel cell. So PV array and fuel cell, they are going to act as a sources of energy, right? So this PV array and fuel cell, and we have supercapacitors, battery, which are part of the energy system, right? So they basically act as energy buffers. So supercapacitor and battery. Of course, they have a different time constants, the battery and supercapacitor. So supercapacitor has a high energy density, whereas a battery can go with the high power. So that is okay. That is a different story. Now we have these kind of sources. Then we have a common bus. We can have a common bus. Then we have the power quality controller if we need, or then we have the PCC. Then we might have a main grid, a local bus. So basically, all of these sources and the loads needs to be synchronized, and they should go hand in hand. Only then we'll be able to maintain the stability of the grid. Okay. So this PV array. So if you want one thing that needs to be observed here is that all the sources that are there, they need to be connected. If at all we have a common AC bus, they needs to be connected via inverters, right? Of course, it's a bidirection. It could be DC, and if at all, since PV and fuel cell will not have a reverse, so this DC to AC converters that we have for supercapacitor and batteries should be bidirectional in nature, whereas these could be unidirectional. So, anyways, whether it is unidirectional or bidirectional, they are going to act like an inverter. So, at one point of time, they have to convert the power available on the DC side, and they have to push it onto the AC grid. And this is possible only by the inverters. So, having said that, so that means in a microgrid, one of the indispensable part, or that is something that we cannot take away out of the microgrid, when we have sources like PV, fuel cell, or battery, is the inverter. So that much importance is there for a inverter, and it is one of the critical component that needs to be designed properly, and it has to be included in our system. So that is the main focus. That inverter being the central part, we'll try to explore more of inverter, and then we'll slowly build on to the multi-level inverters. What is the need to go for a multi-level, and what exactly we do? Okay, right. Now types of PV inverter. So when we look at in this block diagram, if you see, it is simply named as DC to AC inverter, converters, or inverters. So what are the various inverter configuration that we can have in a system depends on the power capacity we are trying to, the power that we are trying to harness, right? And the way we are trying to connect. So especially now on, we'll try to concentrate only on the PV fed inverters. Okay. So PV fed inverters is a central part of the any given microgrid. So we'll try to concentrate more on a PV inverter. So types of PV inverters. So as you can see from this image, you can have variety of configuration, right? So this yellow box, what you see is the PV panel. So you can have a modular configuration, so which is shown here. So why is it called modular? Because we have a dedicated DC-DC converters for each of these PV panels. There are many panels that are connected in series, okay? And then it forms an array, and we have a DC-DC converter for each of the array. Okay. Now these DC-DC converters are connected to a common DC bus. Okay. Then we have inverter modules, right? We have DC to AC that are going on. Now there are many inverters. Just to make sure, if at all we want to have a single inverter, and if it has to process all the power from this PV, the size of the inverter would be very large. So that is the reason that we may go for a single inverter, or we can have a multiple inverters which are in parallel trying to extract power from the DC bus. So what is the advantage with that? So the advantage is that if at all a single inverter fails, still we have the rest of the inverters. Of course, they have to take on a higher load on them, but still they will be able to draw or dump the power from DC bus to the grid. So that is the main advantage of a modular configuration. So the moment we have modular, that means the system is having a higher reliability. Even though that means even though there is a failure, it is going to sustain operation it is able to continue the operation. Okay, so that is a modular configuration. Okay, here what is the function of this DC-DC converters? One of the major function is to do the MPPT for each of the means, of course, for the PV array, and the DC bus voltage in this case would be controlled by the inverter. Okay, then we have a multi-string configuration, what you see here. So this is what I was talking about. So this is similar to modular configuration. The only difference is we have a single big inverter sitting over there that takes power from all the DC-DC converters, and then it converts into AC that will be sent to the grid. So this is called a multi-string configuration. So one of the challenge is that if at all the inverter fails, then this entire system has to be shut down, right? So even though we have PV generating power, DC-DC converters are working fine, still we don't have the central link, the bridge between DC to AC, right? So that is one of the challenge. But however, this would be lesser costly as compared to this. Anyway, cost is a different issue. Then you have a string configuration. So in string configuration, what we have many inverters. We have eliminated the DC to DC. We have a direct inverters that are there and that will be connected to the single phase. So the DC-DC converter itself is eliminated in this case. So the inverters itself will perform the MPPT operation. Okay. Then you have a centralized configuration, which is similar to multi-string, but in this case, what we have PV arrays connected in series parallel, and that goes as an input to the inverter, and we have a three-phase grid. So this centralized configuration, again, the problem is the inverter has to be rated for full power capacity of the PV panels. Okay. So that is the centralized configuration. Then you have the module configuration, or it is also called as a micro inverter, where we have for each PV, we can have inverters that are small in size because their power rating is dependent on the panel rating, which would be much lesser compared to the system power. Okay. So we have an inverter for each of the panel, which will be very small, that is typically back mounted on the PV panel itself. So on the back side, we are going to have these inverters and they'll run in parallel. Okay. So they'll be connected to the single phase. So each of these configurations have their own advantages and disadvantages. Okay. So when the power level is not that high, then typically we can go for a micro inverter, which generally will be connected to a single phase grid. So when the power level is higher, we have to go for a three-phase grid, in which case it could be centralized configuration, or it could be multi-string, or it could be modular. Okay. So basically, these are the broader ways in which we can connect our PV panels into a grid. Okay, so what you see here again is inverter. So inverter is always there in the system the moment we have a microgrid, or because we have a AC grid. Until unless we have a AC grid, so inverters are required, and we cannot take out inverter from our system. Okay. So which configuration should we choose? That depends on the power range. So that is what is given in this table. So power range, like up to 1 kilowatt, we can go for a micro inverter. And uh, there is a question on this. Okay, let me take up the question at the end. So because I have to go back to the chat again. Okay, anyways. So 1 kilowatt, we have a micro inverter, and typically they are used in residential application. And for the power rating 1 to 30 kilowatt, we go for a string inverter, which could be rooftop. 10 to 100, we have a multi-string that could be that are generally commercial, and 100 to 5 megawatt, we go for a central inverter where we have a solar farm. So all the solar farms, we go for a central inverter, and for above, we go for a multi-level or a MMC configuration. So these micro inverters are very popular since they typically we use in residential, and also even the string inverters, they can be on our rooftop. Okay. Right. Now, shifting from centralized to distributed generation. Now, what are we expecting from our inverters? So that is the next question we'll try to answer. So now we know that whenever you have a PV and grid, inverters are essential. And what are the desirable features that an inverter should have? Right. In order to know what are the desirable features, we should know what does the system need without an inverter. Okay. Now assume you have a PV and you have a grid, and we know that the PV generates DC, and there is always a requirement that many PV panels has to be connected in series in order to build or in order to have a whole voltage that is sufficient enough so that the power goes from PV side into the grid. Okay. Now, often what happens when we have many PVs in series, there is always a mismatch that would happen. So in order to avoid that, what we do, we have to somehow make sure that our system has a voltage boosting capability, right? What is the advantage of that? So that we need not have to connect many PV panels in series. Okay. So in order to reduce that, we have to somehow bring a voltage gain in our system, and this can be done in two ways. That is, either we can go for a AC boosting or we can have a DC side boosting. Okay. So when I say AC boosting, what does that mean? You have some PV panels and you have an inverter, right? Then you have a filter, and the voltage that we generate would not be sufficiently high to pump power into the grid. Okay, then what we do? We use a transformer so that we are going to step up the voltage, and then we'll try to synchronize them. Okay, so that is, and since the transformer is directly coupled to the grid, the transformer has to be low frequency, that is 50 hertz transformer, and its function is to make sure the voltage matching happens between the two. Okay. Now, if we don't want transformer, because as we know it is a bulky, right, and it is going to increase the size of our overall system, we will go for, or we can go for a DC side boosting. So what we do here, we have a DC-DC converter, which is going to boost the voltage that comes from the PV, and it dumps onto the DC link capacitor. Then the inverter is going to invert and connect to the grid. So there is no need for the transformer because the DC voltage that is available at the input of the inverter is already sufficiently large. It is high enough for the power to be dumped. Okay. Now, the question that we need to ask is, so these are the two ways. What if our inverter itself has the ability to boost the voltage, right? So since we know that either it has to be AC side or DC side, what if the inverter itself can boost the voltage by some gain, right? By some gain, so that what is the advantage? We can eliminate that. We don't need a transformer, and also we need not have to have a DC-DC converter. So the inverter itself should have a capacity to boost the voltage. When I say boost, what does that mean? It has to generate an output voltage peak which is higher than the PV peak voltage. Now assume the voltage on the DC link is 100 volts. Then if we assume the gain of the inverter to be 2, then the output AC voltage that what we get here should have a peak of 200 volts. That is what I'm trying to say. Okay. So that is the first thing. Second, what if the inverter has the ability to do multi-level operation? So we'll see what is the advantage of that in the later slide. So these are the two characteristics that we try to combine in an inverter. So the inverter should have a boosting ability, and the inverter should have a capacity to go for a multi-level operation. So these are the challenges that we try to address, that employ transformers for the matching voltage requirement, so that we need to eliminate, requires more number of storage battery in order to meet the voltage requirement, that also then require bulky inductive and capacitive filters in order to achieve high power quality output voltage. So by going for a multi-level operation, we'll be able to reduce the filter size significantly, and by having a boosting, we'll be able to reduce, or we can eliminate the transformer or a DC-DC converter. Okay. So that is what we are trying to see. Can we have a structure that can do both? Next, one of the important things that we need to know is about the PV grounding. Grounding. Okay. Now, what happens often? the PV panels, what we have, they have like several exposed parts which are non-current carrying metals, or they are conducting parts, right? So that there we can divide the PV parts into two categories. One is non-current carrying and another is the current carrying conductor. Okay. Like what are the non-current NCC? That is your non-current carrying metals like the module frame, rack, metal enclosures, distribution panels, right? So those are all the part that goes for NCC. But if at all there is some fault or something, there could be a connection between the current carrying conductor and NCC. So that would further cause a problem in the as far as the operational safety is concerned. Okay. So how to avoid that? Okay. So in order to avoid that, what we do, we are going to connect all the non-carrying, non-NCCs, that is non-current carrying conductors, and we are going to have a EGC, that is equipment grounding. Okay. Equipment grounding for the safety purpose. Okay. That is called as equipment grounding conductor. Okay. Now, and this is essential that if at all and we have a standard for this, which says that the grounding is mandatory. At least this EGC is mandatory for a ground for safety operation of a overall PV plant. Okay. Now, what is the problem with this grounding is that the moment we ground, what happens? There is a PV parasitic capacitance, which means it is not a physical capacitor, but the panel has a very large surface that is exposed, and there forms a capacitance, distributed capacitance at the whole. At the overall, it is going to be uh, having a capacitance effect, and this capacitance is going to cause a leakage current to flow. Okay, and that path will be through the grounding path, which we have provided for the safety purpose. So that is what is written in this table there. We have two kinds of grounding, that is equipment grounding and system grounding. So you can see that what are the equipment grounding part, it is the racking, junction box, etc. System grounding is the actual DC or AC circuit conductor, that is a negative wire. Okay. So why are these supposed to be grounded? So that EGC is required to make sure all the metal parts stay at 0 volt and there won't be any shock even if someone touches it. And system grounding is going to stabilize the electrical and helps the inverter to detect ground faults. Now, keeping the safety aspect in mind, the moment we ground the PV, and if you don't, or if you try to operate PV ungrounded, the chances of hazards is very, there will be very high chance of fire hazard or something. So that is what is reported even in literature. There is many cases that have been studied, and that is one of the major reasons. In keeping that in mind, grounding of a PV becomes essential. The moment PV is grounded, what happens? The parasitic capacitance is activated. So it activated in the sense it gets a path through the ground. Okay. Now, what are the problem with this parasitic capacitance? We'll see soon. So a PV equivalent or a PV with a grounded or EGC grounded is represented by this. So this is what the equivalent circuit or the equivalent model look like, that if you have the negative DC rail of the PV, you have a RS and RP, and you have a leakage current capacitance. Okay, so this is the equivalent model of a PV. Now, what are the challenges? So just now I told that in order to keep the safety or keeping safety as the main concern, we have to ground a PV system. But that causes or that provides a path for the parasitic capacitance. So from where does this capacitance come from? So this image, what you see here, you can see that you have a PV panel frame, right? Then you have many capacitors, and this capacitance, what you see here is of larger value, right? So then we have this capacitance is basically because of the potential difference, and you have an insulator kind of a material in between. Okay. and module frame. There are many distributed capacitance. Overall, at the end, you will have one lumped capacitor that comes between the PV array and the ground. Okay. So this capacitance, what you see here, CPV, this is the equivalent circuit. So you have a PV, this is your DC link capacitor, and this is your inverter, and this is your inductors and the grid, and you have your PV parasitic capacitance that comes between the negative DC bus or the negative PV terminal and the ground. Okay. So this is a physical grounding that we have done for the safety. Okay. Now, so this parasitic capacitance, what is available now is going to provide path for the current. This is called as a common mode current, or it is also called the leakage current. So this leakage current is going to cause a problem. What is the problem? It is going to distort the grid current. That is the first problem, that because this current is going to flow out of the inverter terminal, and it is not a circulating current. The moment common mode current or the common mode current means it is going to flow only in one of the terminals or one of the line, and it will not come back with the other, right? So it will go from A grid to ground, then we have another part going from grid B, then ground. So that is how it is going to circulate. Okay, but it is not going to circulate in the return path. From the origin path, it will directly go to the ground. So that is the common mode characteristics of a leakage current. Okay. So what does it do? It is going to add on to the grid current. So that way it is going to distort our grid current. So which we are trying to maintain. The grid current we are trying to maintain at a high quality of THV less than 5% that we are trying to inject into the grid, and this is going to distort that grid. That is one thing. Second thing, it is going to cause mal-operation of the RCDs, that is your residual current detectors. So often they may get tripped, thinking that there is a ground fault that has happened. So even that is a issue. Okay. So how to tackle this leakage current is one of the major uh, concern. Okay. So we have to, whenever we have an inverter connected to the grid, we have to go for, or we have to satisfy the standard, that is VDE0126, right? So according to which the leakage current should be less than 30 milliampere. This is the peak value, right? And the RMS should be less than 300 uh, milliampere. Okay, 300 milliampere is the value that is decided in the standard, and we have to limit the common mode behavior, and we have to improve the power quality, and we have to avoid apparatus malfunctioning. So these are the challenges that we need to take care in on our inverter side. Okay. And of course, inverter is not the reason for this. The reason is the capacitor, the the parasitic capacitance. But through inverter, we will try to address this issue. Okay. Now, the total common mode voltage that is going to be experienced, or that is going to be imposed on the parasitic capacitance, is given by any common mode voltage. We always define, if you have a any two terminal system, the common mode voltage is defined as the average value or average voltage of the terminal with the common point. So in this case, the negative DC bus is the common point. So VAN plus VBN, because those are the output terminals, by 2. Since we have two output terminals upon 2, that is the averaged value. So that is the common mode if L1 equal to L2. And why have we splitted? Generally, if you look at any grid connected inverter, you have a single inductor grid, and you will not have anything over on this line. But since we know that the common mode current flows in both the lines, and it is not that the returning path, what happens to the actual? Assume we don't have this parasitic capacitance, then how does the grid current flow? It will flow to grid, then it will come back during positive half cycle. During negative half cycle, it is going to flow this way. So ultimately, it is going to originate from one of the output port, and it will come back to the other output port, and it is going to reverse. Okay. So that is how the differential current or the actual grid current flows. But the common mode current is not going to do that way. It is going to originate from one of the port, and it will go to ground, and it will take another path, right? It is not going to flow in the opposite direction. So you'll have a current that goes from A to ground, then you'll have a current goes from B to ground. So if you put inductor in only one of the leg, then we will be able to attenuate the common mode current only in this part or the path, right? Whereas this path, there is no attenuation. So that is the reason we have to split the inductor into two. Whatever the design you are going to make, like for example, if the design says you have to go with a 3 millihenry inductor, then we are going to split 1.5 and 1.5. So this way, in both the path, we are going to attenuate the common mode current. Okay. So that is the reason we have two inductors over there, which is to take care of the common mode current. Okay. Anyway, just by having these inductors, we will not be able to means completely attenuate the common mode current. Right. So what are the solutions for this? So there are two ways to approach this problem. One is the topological approach, which we work on, and other is the PWM based approach. So what is in the PWM based approach, what is the main objective is to come up with a modulation scheme which will make sure that this total common mode voltage, what you see here, is going to remain a constant, almost a constant. So what does that do? If this common mode voltage is maintained constant, basically this is the voltage that is going to influence this capacitor. And we know that the current through capacitor is given by C into dV by dt. Okay. So if you maintain this common mode voltage a near constant, dV by dt becomes almost zero. So if dV by dt becomes zero, then current through this capacitor is zero. So that way we'll be able to attenuate the common mode current. That is through modulation. So you can come up with some kind of a modulation or a PWM scheme so that the overall common mode voltage remains a constant. Okay. What is the other way is the topological approach, which we do. The topological approach is classified into two types. One is called midpoint based solution, and other is called common ground based solution. Okay. So sorry, in midpoint based solution, what do we do? So instead of what we do is the neutral point of the grid, what is there, is will be connected to the DC link midpoint. That is this single capacitor over here will split into two, and that midpoint will be used as one of the return path for the current. So ultimately what is going to happen? This parasitic capacitor now comes in parallel with the DC link capacitor, which has been split. Okay. The moment that happens, so we know that in an inverter on the DC side, the capacitor is large enough. Okay. And the voltage across this capacitor is almost a constant at VDC by 2 is the average value. And you would see a small 100 hertz ripple that is superimposed on VDC by 2. So now that is the voltage that also gets applied across this CPV. So now we can have the voltage across the DC link capacitor uh, has two components. One is the DC component, which is VDC by 2, and another is 100 hertz ripple component, which is of very small value. Okay. Now this capacitor is going to act like an open circuit for the DC component, of course, VDC by 2, and the frequency of the ripple, that is 100 hertz. Since the frequency is very, very small, the reactance offered by the capacitor is very large. So in both the case, means with that, the current that is going to flow through the parasitic capacitance is going to reduce significantly. Okay. So that is called a midpoint based solution. But what is the disadvantage here? The disadvantage is the DC link. The moment you use the midpoint, the output voltage that you can generate for a given DC voltage is going to be half. Or, in other words, we say the DC bus utilization is only 50%. What do you mean by that? Like, if the DC link voltage is, say, 100 volts, if you don't use the midpoint and you use like a structure similar to this, if this is 100, the peak voltage that you can generate here at the inverter output is 100. Okay. The moment you use the split or the neutral point uh, as a return path, that becomes equal to 50. That is the maximum. Okay, 50. So that way, even though you have a 100 volts DC bus, the peak that you can generate in the AC is only 50. So the DC bus utilization goes to 50%. Okay. Then we have the common ground type configuration, in this case, what we do, instead of connecting it to the midpoint, we are going to connect the AC grid neutral with the negative DC bus. So that is what is done here. Okay, so you can see the neutral point of the AC grid is connected to the negative DC bus. So as it is visually clear that the moment you do this, the capacitance, the parasitic capacitance is ideally short circuited. Okay. So we have a short circuit appearing across the parasitic capacitance, and this is going to completely eliminate the effect of parasitic capacitance. Whereas in this case, the parasitic capacitance is there, but the leakage current is reduced. In this case, it is eliminated. So we'll see both of this, how we have tackled this issue. So as of now, let us quickly summarize what we have seen till now. So we started from basic, what does the microgrid look like? Okay, let us quickly summarize. So we have, what does the microgrid look like? You have inverters, right? So then we saw what are the typical PV inverters structure that we have, okay, and what are the various power ratings. Then what is the need, or what are the desirable features from an inverter, right? So if at all you have to eliminate transformer or a DC-DC converter, then we should have an inverter which has an ability to boost the voltage. Okay. Then we saw what is the need for grounding and why is it essential. And we also saw the moment you ground, what is going to happen. And what is the additional challenge that comes into picture? That is your parasitic capacitance. And how are we going to tackle it? Either we can go for a PWM method, where we will be able to essentially will try to maintain the voltage across this capacitor constant, so that dV by dt is lesser and there is a low leakage current flowing. Or we can go for, ultimately we are doing the same in this case, but structurally we are trying to do that. In PWM, the structure remains same. We are going to play with the pulse width modulation. In case of a structural, that is topological approach, we are going to play with the way we are building the inverter, or the way we are building the structure of the inverter. Okay, next, understanding common mode voltage. So we'll take up some examples to see how a PWM method is going to, means both we'll try to address that how a PWM method is going to impact your common mode voltage, and how structurally we can modify a given inverter so that the leakage current is reduced. Okay. Now, this is the first example that we'll try to see. This is a well-known architecture of inverter, which is popularly known as a H-bridge inverter. Okay, so you have four switches: S1, S2, S3, S4, and D1, D2, D3 are the anti-parallel diodes that are there with the IGBT. Okay, then you have L1, L2, as already told, that we have split the inductor into two parts so that the common mode current is means attenuated properly. Okay, then you have your grid, then you have your PV. Okay. Now, what is that we are assuming? It is not that we are assuming, there is a parasitic capacitance that gets connected from the grid to the negative DC bus that I'll show in the simulation. So you have a connection over here. Now, this inverter can be operated with two popular modulation technique. One is called as a bipolar modulation, and another is called unipolar modulation. Okay. Now, what is a bipolar modulation? So in bipolar modulation, you have a carrier, high frequency carrier, whose frequency is going to decide what is the switching frequency of this device. So if at all we are asked what is the switching frequency of the inverter, who is going to decide? That is decided by the carrier frequency. 10 kilohertz, 20 kilohertz, 50 kilohertz. That is what it means. Okay. Then you have, that is your V triangle. Then you have your VM corresponding to the modulation signal, which is the fundamental voltage that we are trying to synthesize through this inverter. Okay. So ideally, what should our inverter function like? Our inverter should function like a synchronous generator. Okay. Because that is what we have traditionally, that is what we know, right? So synchronous, whenever we say an AC generator, or whenever we visualize an AC signal or an AC waveform, from where does it originate? It comes from an AC generator, right? So an alternator or a synchronous machine. So what is the difference here is, in a synchronous machine, we are going to, the machine is free to rotate in the air gap, right? You have a field poles that is going to generate uh, means the flux is it is going to generate your MMF, which is constant, right? And it keeps on rotating at synchronous speed, and then it is going to induce EMF, and all those things happen. So, and that MMF is very freely, it is moving in the air gap, and that is the reason we have a sinusoid which is very smooth in nature and that is being generated. Because we know that any sinusoid can be represented by a rotating vector, that is nothing but a phasor. Okay. So in a generator, the reverse is happening. You have a phasor that is rotating, so we are getting a sinusoidal waveform. Okay. It is exactly the reverse. In basic electrical, we study that any sinusoid can be represented by a phasor. In a machine, the reverse happens that a phasor is going to generate a sinusoid. It is the same thing. Okay. But an inverter, in an inverter, we don't have any rotating part because we have a static device. Okay, these are all semiconductor devices. So what does the inverter know? An inverter know to only the switches that are used in the inverters. They know only one function, either to turn on or turn off. Okay, so it does only this that either to turn on or they'll be off. So this on and off is a discontinuous function. It is not a continuous function, right? So it is happening in a discrete way. So this on and off we are trying to do, and what we are trying to generate is a sinusoid which is very smoothly varying, and this can never happen, right? So using a discrete function, we cannot build a continuous function. So what we do instead is we'll try to have a sinusoidal function on not an instantaneous basis, but on an average basis. So that is what the overall means the overall PWM, the idea comes from, right? So anyways, we know that by on off or a discrete discontinuous function, we cannot have a sinusoid. Then what we'll do, the best possible is you generate a waveform whose average value, or at least on an average basis, it should track a sinusoid. So who is going to decide how well it will be tracked? By the carrier waveform. Okay. Higher the frequency, the average value will be very much nearer to a sinusoid. So that is the overall idea of a sine triangle PWM. Okay. So in bipolar modulation, what we do, you have a single carrier and you have a triangle. So whenever the carrier waveform is greater than the triangle, you are going to switch on S1 and 4, so diagonal switches. Okay. And whenever the triangle is on the upper side of the sinusoid, you are going to generate you are going to turn on switch S2 and S3. Okay. Now whenever S1 and S4 are on, this terminal 1 is connected to the positive and 2 will be connected to negative. So you are going to have DC voltage, that is UPV, that is your U12. U12 is the output voltage, which will be equal to UPV. Okay. And whenever S2 and S3 are on, the terminals are reversed. So you are going to have minus UPV. Okay. So that is how we have generated an AC waveform. So even though the voltage U12 is not a sinusoid, if you calculate the average value of this waveform in every switching period, and if you try to plot that, it would look like a sinusoid. Okay. You can see the average value over here, right? And you can see the average value. So this one complete on and off is one cycle, right? One. So if you do the averaging basis, that would represent the sinusoid. So that is called as a bipolar modulation. Why bipolar? Because the output voltage has two levels. Either it is UPV or it is minus UPV, right? It has to. Like for example, UPV is 100, the output will swing between plus 100 and minus 100. And the variation, if you look, it is going to, at the starting, you'll have a smaller pulse, then gradually the pulse is going to increase, then again it is going to reduce, just like how the sinusoid varies. Now, there is a problem with this bipolar modulation. We'll see what it is. Then, on contrary to this, we have unipolar modulation. As the name itself indicates, the output is going to have two levels, but instead of swinging from plus to minus, we'll swing from plus to 0 or 0 to minus. So we have an additional level in the output, that is 0, or additional voltage level, okay, which is 0. Now, what is the advantage? You can see that if you look at these two waveforms, now, okay, before that, how are we able to generate a 0? Because if you turn on either of the upper switches, S1, S3, or the lower switches, S2, S4, in both the case, 1 and 2 terminals are short circuited. Okay. So the moment you short circuit, there is a zero voltage being applied. Short circuiting the load, or on this side, the source is disconnected. If you turn on these two, it is short circuit, but these two are off, so source is disconnected. Okay. So with that, what are we trying to do? So this is how the gate pulse pattern look like. We'll not get into the detail. So this is how the output look like. Okay. So what you see here, in the positive half cycle, that is of our modulating wave, the output is either 0 plus, or in the negative half cycle, it is or 0 minus. So if you look at this waveform, this is very, very nearer to our modulating waveform, which is actually what our inverter should generate. So ideally, I want this, the output should look like this. So for this waveform, this output, whatever I am able to generate, is very much nearer rather than this. Okay, because in the one half cycle, the output is never going to, or this waveform is never having any negative value. But in this case, we are switching to the negative part, or we are generating minus UPV, right? So waveform wise or look wise, this is very, very nearer to my waveform. So this voltage waveform, what you see here, has a better harmonic performance, right? So the harmonics, if you look at, which harmonics are nothing but the undesired the components in the output. So in this waveform, it will be, well, the undesired are very much taken care of as compared to this bipolar modulation. Okay. Now, let us define two terminologies. One is called as the differential mode voltage, and another is called the common mode voltage, UDM and UCM. Okay. So what is the differential mode voltage? That is U1n minus U2n. That is 1 to n, you measure the voltage. Then 2 to n, you measure the voltage. The difference of that is your differential voltage. That is what we are referring to as the inverter output voltage. Okay, because inverter output terminals are 1 and 2, and voltage is always differential. We always express voltage with reference to something. It is not absolute. If I say 100 volts, that means there is some reference point with which I am measuring 100. Okay. So U1n minus U2n. That is your differential mode voltage. Now, what is common mode voltage? Same definition, U1n plus U2n. You have two terminals, so divided by 2. This is your UCM. Okay. Now, if at all you calculate what is this UDM and UCM for various switchings, right? Like for example, in bipolar modulation, you have one of the operating modes when U1n is UPV and U2n is 0. So when does that happen? When switch S1 is on and switch S4 is on. Okay. When these two, try to see, when these two switches are on, these two are off. Okay. They are complement. So when this is on, U1 to N, this is off. So U1 to N is same as UPV. When this switch is on, U2 to N is short circuited, right? Switch is on, short circuit. Switch is off, open circuit. Okay. So this is your U1N and U2N, that is UPV and 0. So you can see UDM, that is the differential voltage is UPV, and common mode voltage is UPV by 2. Then you have another mode that is 0 and UPV, and you have another 0 UPV and UPV and 0. So where the output is going to be, the differential is minus UPV, then you have minus UPV and UPV. Now for the same UPV, you have two switching states. What does that mean? Switching states in the sense you have two levels, because in one case the current would be going out or the current would be coming in. We don't know what is the power factor. So in both the case, you will have UPV and that, and the same good thing goes with the minus UPV. And what is interesting to note here is that the common mode voltage is constant, UPV by 2. Whatever is the inverter switching state, whether it is UPV or minus UPV, the common mode voltage is constant in case of a bipolar modulation. Okay. And if you look at the unipolar modulation, for these are the output levels that you have. That is, you have three levels of output: UPV, minus UPV, and 0. Okay. And you can see that the common mode voltage is going to swing between the level UPV by 2, UPV again by 2, and 0. So what does that indicate? That shows that the common mode voltage performance is good in case of a bipolar modulation, because it is a constant in case of bipolar modulation. Whereas in unipolar, it is swinging, it is changing. Okay. This change is going to cause a leakage current, right? because the moment common mode voltage changes, there is a dV by dt. In this case, the dV by dt is 0. Okay, UCM is constant, so dV by dt is 0. In this case, dV by dt is changing. Now the inverter goes from 0 to UPV. It switches 0 UPV, 0 UPV, 0 UPV. It keeps on switching. Only difference is the pulse width is going to change, but it keeps on switching. So whenever that switches, UCM is also changing from UPV, UPV by 2, and UPV, UPV by 2 and 0. So that is dV by dt. So that causes a leakage current. That is bad. And what about harmonics? If you look from the harmonics point of view, bipolar is bad because the THD, the total harmonic distortion. If you try to analyze the waveform, see, basically total harmonic distortion is what? It basically indicates the waveform what we have generated is how far from a sinusoid. Okay, you have a sinusoid that you wanted to generate, but we have generated some other waveform. What is the difference, right? If you subtract this from sinusoid, what that gives you the harmonics. Higher the harmonics, higher will be the THD. Okay, so in a bipolar, the waveform what you have generated is not so nearer to your sinusoid as compared to your unipolar voltage. Okay, so that is going to give a bad harmonic performance, whereas in unipolar it is better. Okay. So that is the analysis as far as the common mode voltage and the differential mode voltage is concerned in case of a full bridge transformerless inverter, or the classic name is the H bridge inverter. Okay. So next I'll show the three circuits at once, then we'll go to the simulation. So I hope, I think it's been almost 1 hour, so I hope everything is going fine. I'm audible and the things are clear. Can I get any acknowledgement or something? Is it fine?
Yes, sir. It's audible.
Okay. Okay. Now, so what we saw is, as far as the modulation is concerned, again there is a trade-off. So that is how a PWM is going to affect your UCM. That is what we have seen. The structure is the same. The structure is the same inverter. What is the difference? In one case, the common mode voltage is higher, or the dV by dt is higher, whereas in another case it is lesser. It is because of the PWM we have incorporated. So can we have now out of these two, the unipolar and bipolar? Unipolar is better because harmonics are less. The moment harmonics are less, the filtering is going to reduce significantly, right? So keeping that in mind, people started using unipolar, right? But the problem is with unipolar, the common mode voltage performance is going to be deteriorated. So how to tackle that? So in order to answer that question, that I want a unipolar output at the inverter terminals, and I also want to reduce the common mode voltage. So that is where the topological play started. Okay. So what they did, they started adding elements into the structure so that we can control the leakage current. So the key idea behind there are several number of topologies. So one of which is HERIC, which is very popular structure. What is the main function? HERIC stands for high efficient, reliable inverter configuration. Okay. So this structure is one of the patented structure by the company, right? So what they did is they connected a bidirectional switch, okay, across the output terminals of the inverter 1 and 2. Okay. So what they are trying to do? They are trying to disconnect the path for the leakage current. Now, from where exactly the path is getting created? You have this grounded here, right? The AC point is grounded, and you have a capacitor that originates from here and that gets connected here. So the overall idea is, if we can break this path during the process of switching, then we can reduce the leakage current, because ultimately you are disconnecting the inverter or you are disconnecting the common mode path for some time in a switching period or in a cyclic period. Okay. So from that idea, they used switch S5 and S6. This is called as AC decoupling. Okay. So why is it called AC decoupling? Because on the AC side, we are going to isolate the PV from the grid. Okay. Now, how are we isolating? So you can see here that when U1N is UPV and U2N is 0, right? Output is the differential voltage is UPV and the common mode voltage by the same definition it is UPV by 2, right? Now the moment you want to generate a zero output voltage here in the output means this part in the output, whenever you want to generate a zero, what you do is you, of course, you are going to connect like your S1 and S3 are on. So you can see here, right? So whenever you want to has to be 0, right? Then what you do is you turn on the switch S5 and S6. So that is going to ultimately short circuit this path. Okay, ultimately you are going to short circuit the path. Okay, then if you look at your switches, the rest of the switches, your S1, S4, okay, and S2, S3, they are open. So you are going to open all these 4 switches and you are going to switch on the bidirectional switch. So that is going to ultimately cause 0 and the PV is disconnected from the path. The moment PV gets disconnected, the leakage current becomes 0. Means the leakage current path is broken. Okay. And this happens during every time the inverter generates a 0 output voltage level. Okay. So whenever inverter output voltage becomes 0, you disconnect the PV by opening these 4 switches and closing this switch S5, S6. So that is the basic idea. When this happens, the UCM is undefined because we don't know what is the voltage V1N and V2N, but ultimately it is not changing. So you can see that UCM is almost remaining a constant. So this is the basic idea behind Herrick structure. And next is the H5 topology, which is also popular, which has been commercialized by the SMA industries, right? So this H5 is the advanced or the improved version of Herrick. So what is happening here is the disconnection is being done by only one of the switch, that is your S5. Okay. You have a switch S5 that is connected on the DC side. The rest of the H bridge is same. Even you can see here, the H bridge remains same. We have only added one bidirectional switch. In H5, the H bridge remains same. We have added only one switch S5. Okay. And this is called as a DC decoupling because from the DC side, we are going to disconnect the PV. Okay. Now, again, the same concept. Whenever inverter generates a zero output voltage level, right, you open this S5. Okay, so you can see. So whenever S5 is open during this part, if you try to see, whenever output voltage is 0, S5 is open. This is open. The moment this opens, the common mode path gets broken. Okay, and you can see that the common mode voltage remains. Of course, we don't know what is happening in this uncertain period, but the UCM is almost remaining a constant. What is the advantage of this S5 compared to H6? Sorry, your H6 or Herrick, both are same. Is that in Herrick you have added two switches, whereas in H5 you have only one switch. So that is the advantage. Efficiency wise, this performs better than your Herrick topology. So that is a very basic version how the structure started means getting popularized. Okay. So based on this, there are several innumerable number of topologies which have played on a variety of concepts or variety of parameters. There are very like I will show in the summary. I will show those. Okay. Then you have the neutral point clamp. Okay. So all this is the H bridge variation. Then in neutral point clamp, something interesting happens is the moment you, as I already told, the moment you have the neutral point as a return path, right? As a return path, the common mode voltage, what you see here is equal to UPV by 2, right? So don't, means as of now, try to concentrate on what is happening to the common mode voltage. It is UPV by 2. So we know that the moment it becomes constant, dV by dt is 0, right? Whenever the inverter switches between the levels, right, dV by dt remains 0, means 0, and the leakage current would be attenuated. So that is the advantage. So without adding any switches or without breaking any path, the simplest way to attenuate the leakage current is to use the DC link midpoint as the return conductor or the return path. But what is the problem? The moment you do this, the DC bus utilization is 50%. we have reduced it by 50%. Okay. So this is what I was talking about, summary of some of the CMV techniques. So based on the decoupling type, so that I told. So whether it is on the AC side or the DC side, you can see there are variety of topologies. On the DC side, you have H5, H6 version 4, 5. Then what is the kind of switches that you have used, whether they're unidirectional or bidirectional path. So these are all the topologies. So whatever you see, like some 15, 20, what you see here, these are all the structures that have been worked upon, keeping the concept. What is the concept? Either you decouple the AC side or DC side. But what do you mean by decoupling? You have to disconnect the PV whenever the inverter generates zero output voltage. That is going to reduce your leakage current. Or you go with a neutral point plant. Right? So now I just want to show some of the simulations. So let me start. Just a second. I'm just trying to. Okay, let me open. Can Anupam, is my MATLAB visible?
No, not yet, sir. Only slides are visible.
Okay. Second. Now can you confirm? Like,
Yes, sir, yes, visible.
okay, right. So let me start with the chart. Sorry, it is taking more time. Just a second. Okay, meanwhile, if there are any queries till now, you can ask so that, okay, it has opened. Okay, right. So this is what I was talking about. So let us take the bipolar as an example. Okay. So what you see here, you have the H bridge, right? You have the H bridge, then the, okay, I think just a second. The MATLAB has crashed. Mm, okay, right. So what you see here is the bipolar structure, right? So we have our inverter, then we have the DC bus, and then this is your common mode attenuation setup. Then you have a load. So this is a filter, C filter that has been used, right? Then this capacitor, what you see here is the parasitic capacitance that is connected between. So that is what I was saying, that this is connected between the negative DC bus and the grid. In this case, it is not grid connected, of course, and the neutral point of the load. Okay, so this is the capacitance, and typically the capacitance value goes from 20 to 100 nanofarad per kilowatt. That is the typical range. And this again, it changes. This is not a fixed value. The capacitance value depends on the way module is, the panel is, like the dust, whether the module is having a dusty environment or moisture, all those things are going to affect the capacitance value. So anywhere in the nanofarad of the range 20 to 100 is fine per kilowatt. Okay. So this is the capacitance. So let us run this. So this is the PWM that the scheme that we have used. So we'll just try to see the waveforms and we'll try to understand what is happening. Okay. So in case of a bipolar modulation, as we already told, the output is going to swing between plus and minus, right? So output will be either plus VDC or minus VDC, and the common mode voltage is constant. So that is what we have seen. So let us verify whether it is happening, right? Okay. So let me see whether the results. Yeah, okay, result scheme is visible, right? So what you see here is the inverter output voltage, of course, after filtering this is okay. So how exactly the inverter output voltage is there without filtering, you can see over here. So the output is swinging between plus and minus. So it is plus 100 and minus 100, plus 100 and minus 100. So this waveform after filtering is this voltage and this is the current. Okay, so this matches with our inverter output voltage, and let us see what is happening to our differential and the common mode voltage. Okay, let me see this. Okay, so what you see here, the common mode voltage is a constant, right? So that is what we analyze. So VCM, you can see that it is a constant, even though there is a variation. You can see it is varying from 49 point something 999 to 50. So this is almost a constant. Okay. So this waveform, what you see here is a constant. There is some variation, that is fine. So this is our differential voltage, which is swinging from minus 100 to 100, and the common mode voltage is a constant. So leakage current, you can see it is very, very small, like less than point. It is somewhere, the peak is 0.5 into 10 power minus 3, right? So that is our leakage current. Okay. Now the same thing if you look at the unipolar. So let us see the output voltage of unipolar. So you can see what is the difference in case of a bipolar modulation. The output voltage was swinging from minus 100 to plus 100 or plus 100 to minus 100. In unipolar, the output is going to take only two levels in a half cycle, that is 0 and 100. Then you have minus 100 to 100, right? 0 and 100 and minus 0 to minus 100. Okay. So that is the output voltage. And if you look at the leakage current, okay. So this is what it look like. This is your U1N, U2N. This is the definition, and this is the common mode voltage. You can see that the common mode voltage swings between UPV by 2 and UPV. From the table, if you remember, the common mode voltage swings from UPV by 2 to UPV, and that is going to cause the leakage current. You can see here the leakage current is this. So this is our leakage current. So you can see the amplitude is like going up to 0.4, like 400 milliampere. That is the peak. So in case of a bipolar, it was 0.1 into 10 power minus 3. That was the order. Okay. In case of unipolar, the leakage current is large and it has to be attenuated. But what is the advantage here? The output harmonic spectrum is better as compared to bipolar. So this is what we need to remember. So this is the leakage current, right? And this is our differential mode voltage, and this is our common mode voltage. Okay. Now let me close this. So this is the H bridge, what we have. Then let us try to see what is happening in H5. Okay, so the setup remains the same. So you have your 4 switches, the fifth over here, which is used for the DC decoupling. Okay, then the rest of the parameters have remained the same. Let us run. Let us see whether we are able to generate unipolar output voltage or not. Okay, this is the output voltage and current after filtering. Okay, now let us see the leakage current performance over here. So what you can see here, you can see that the leakage current is very much reduced, and you can see the amplitude is maximum is 0.05. Okay, in case of unipolar, it was going up to 0.4, 0.2, right? In this case, it is 0.05, and if you look at the RMS value, it will be much more lesser. Okay, so because whatever it, and this is the differential voltage, and this is the common mode voltage, which is almost nearer to UPV by 2. So the fluctuations, what you see here, right? So you see some fluctuation. So this is what is written in the table as uncertain. Okay, so we don't know which level it is going to swing. Okay, the rest of the level is UPV by 2, that is 50, that is confirmed over here. You can see 50. Over and above, you are going to have fluctuation, that is the uncertain mode, right? And this is the leakage current. Okay, and output voltage is unipolar. So this is your H5. Then we have H6, that is your Herrick. So Herrick, as we know, right, you have two switches on the AC side. So this is AC decoupling based. You have two switches, and we'll not get into the PWM details. So let us see whether it is giving a performance similar to H5 or not. So this is your output voltage and current, right, filtered, and this is our, yeah. So this is our common mode voltage. Again, common mode voltage is UPV, if you remember, UPV, and there are some uncertain states. And this is our leakage current with peak value of around 0.015, which is very, very less compared to our unipolar voltage. Okay. And then last we have our neutral point clamped. That is our NPC. So we have our NPC leg, and yeah, we have used this uh, midpoint as the return path for the load as well as the capacitance. So let us see. Right, so this is the output voltage of the inverter, and yeah, so this is the common mode voltage, and this is the leakage current. Okay, so you can see the leakage current seems to be very dominant, but you see the magnitude here, it is into 10 power minus 4. Okay, so it is very, very small compared to our NPC. And what you see here, so this is what I was talking about. In case of a neutral point clamp, the moment you use the DC bus capacitors, the DC bus capacitor voltage would have an average DC value of VDC by 2, that is 50. Okay, here the DC bus line. Over and above, you will have a 100 hertz component that is superimposed. So this 100 hertz is going to means is responsible for the leakage current and the switching action. Of course, you have a switching action superimposed, but dominant is going to be this, right? So that is the reason the leakage current is very small. Okay, right. So now let us shift to the presentation. So what is the screen? Okay. So let us continue with the slides. So what we have, let us summarize one. So what have we seen till now is the two ways of handling the leakage current. One is a PWM way, that is your through modulation, simple, bipolar and unipolar. And another is through the topological way, that is the structurally how we can tackle the leakage current. What is the main objective? Main objective is to make sure that the common mode voltage remains a constant, almost a constant. Okay. So the dV by dt we have to reduce. Okay. Right. Now, what is, so this is what the literature is, means very small portion of the literature, very key points I have tried to cover. Now, what we have done, and I just wanted to present uh, two examples. So we have worked on both, right? We have worked on the neutral point clamp, and also we have worked on the common ground type topology. Okay. Now, when we look at the neutral point clamp, I have highlighted that the moment you use the DC bus midpoint as the return path, the utilization is only 50%. So that is one of the problem that we wanted to elevate. So in literature, there is a concept called as a switched capacitor technique. Okay. So this is the traditional topologies, what you see here. Okay. Traditional topologies. What are the problems? The red color box indicates the problem. What are the problems? 50% distributed utilization and higher component count. Now, why is this higher component count? From where did this higher component count comes into picture? So basically, we are trying to build what are the features we are trying to add for our inverter? We want the inverter to generate a multi-level waveform. So H bridge is can generate a three-level voltage, 0 UPV minus UPV. Now, if we can go for a multi-level operation, we are going to have intermediate levels like 0 UPV by 2 UPV and 0 minus UPV by 2 minus UPV. So this is called a 5-level operation. Then you can go for a 7-level, then you can go for a 9-level. So that is how the multi-level inverter works. So it is going to split, it is going to divide, or the output voltage we are going to have a smaller and smaller step. What is the advantage? The moment you do that, the waveform is going to be very, it is going to be very much nearer to a sinusoid. Okay, because if you look at sinusoid, it is going to very slowly, right? It is not going to instantly go from 0 to Vm. Slowly it is going to change. In a multi-level inverter, also the output is going to slowly change in steps. 0 to VDC by 2, VDC by 2 to V, right? So that tracks the sinusoid in a better way, right? Right. So in order to do that, what are we have to go for more and more switchings. Okay, more and more states, more and more switchings are possible with more and more devices. So that is how the complexity of a multi-level inverter increases. So this complexity can be reduced by something called as a reduced component count multi-level inverters, that somehow we have to optimize the structure so that with lesser components we'll be able to generate a multi-level waveform. So that is the main objective. Okay. So for this traditional topology, then we added, means in the literature, the switched capacitor concept was added. The moment this was done, what happened is the 50 bus DC utilization problem was eliminated. So we could able to go for a 100 bus DC, 100%, sorry, DC bus utilization. So what does that mean? The moment you had switched capacitor concept. So what is this concept? Simple. You add a capacitor in the inverter such that during some portion you can charge that capacitor, and during some other portion you can discharge that capacitor. The moment you charge and discharge, it is going to give you an additional level, and also it is going to provide you with the boosting, because some part you are charging and keeping the energy, and the other part you are going to add that energy plus the source energy. So that is going to increase the output voltage. Okay, that is the switched capacitor concept. Okay. So with that, the 100% utilization is achieved. But there is always a problem with the solution. Whenever there is a solution, there is a problem associated with that. Because there is no 100% solution to any of the problem, right? What is the problem? You have a capacitor in the path. Then whenever there is some switching, the capacitor comes directly across the source, then it is going to draw very large impulse current, because we know CdV by dt is the current. If you try to charge the capacitor at a very small time, it is going to draw larger current. That is the problem. And also higher component count is still prevailing, right? So what we did is we did further refinements into this, and we come up with a solution that is better with some regard, like it has a high power density because we have reduced the components. Through lower components, we are able to achieve this. Limited switched capacitor currents, right? We could able to tackle the switched current, sorry, the charging currents, but completely it cannot be eliminated. We can only reduce that. I'm talking about the capacitor current, not the leakage current. Okay, leakage current is already taken care. and 100% decibel switch capacitor. So this is what we have done. So this is one of the topologies that we proposed. Okay. So this is a traditional topology. What you see traditional in the sense that is from the literature. Okay. One of the few that are shown. Okay. So what you see here, you have a switched capacitor here, right? CFC is called a switched capacitor or floating capacitor, anything. Okay. So this has to be charged to VDC by 2, and here it is charged to VDC. Now this has to be charged to VDC by 2. So this source is VDC to VDC, right? So you can have the levels, right? And depending on that, you can have the levels like what are the levels you can generate? 0, of course, VDC by 2. Then you have VDC. Then you have 1.5 VDC, that is 3 VDC by 2, and 2 VDC. That is how we go. Okay. Now, from where did we get VDC level? If this source is 2 VDC, these capacitor voltages are VDC, VDC. Okay. So you are going to use this capacitor, you will get VDC by 2. If you use this capacitor, you will get VDC. If you add them, you will get 1.5 VDC. Then you have 2 VDC. So that is how it goes. Anyways, we'll not get into the operational details. Now, what is the problem with both of this topology? Is that the switched capacitor, there will be a surge current. Okay. So that surge current, in order to limit, this is the modification that we did. We added a small inductor LR that comes into the picture only during the charging of the capacitor, switched capacitor. So like, for example, you have this charging path, only during that part it will come into picture. So that is going to reduce the charging current, and it is also going to generate a 9-level waveform. It's also going to generate a 5-level waveform. Of course, this is a 5-level. The next version we have 9-level. That okay. So it is going to generate a 5-level wave. So now okay. So these are some of the verification and comparison that we did. Okay. So now if we compare with the traditional active neutral point clamp inverter, and the area was compared depending on considering the same power rating and the capacitors required, their voltage rating. So what we can see is compared to a traditional ANPC, which is a well-established topology, our 5-level inverter would need an area which is reduced by 50%. So that is going to significantly improve the power density. Okay, that is what this table shows. And this is the experimental setup that we built in the lab, and these are some of the experimental results that we got. Okay, so this is the IAC, the switched capacitor current. So you can see even now there is some surge current, but this would be very, very large if we don't go for that LR in the path. And simply placing an inductor is not going to reduce. So this inductor, what you see here, is not like randomly placed, right? So there has been analysis that is done because this inductor sizing has to be done such that within a switching period, it should reduce the current and it should not get into some resonant part. Okay, so that is, anyways, that is a different story. Now, these are some of the experimental waveform, and simply coming up with a topology or proposing a structure is not going to serve the purpose. We have to benchmark, or we have to compare it with the established one. So these are some of the references that are there with which we compared, and this is the cost comparison that we did, considering the variety of devices, switches, rating, and what the commercially available. And this was the cost of the proposed inverter. Okay, so you can see it is not that if you see R3, it is 160, which is lesser than this, but definitely this would have a DC-link utilization of only 50%. Okay. So likewise on the neutral point clamp, that is the leakage current. The moment we have a leakage, the midpoint, the leakage current is already suppressed. So likewise, we have many topologies that are proposed for suppression of leakage current. Okay. Then also we compared the proposed with one of the commercially available inverter from ANPC, sorry, NPC by Infineon. Okay. So this is the topology that they have in order to achieve 100% DC bus utilization. So even in comparison with that, our topology has performed, or it has a performance better than that as far as the switches, the gain, and TVV stands for the total blocking voltage of the devices that is going to ultimately affect your switching losses, right? So the proposed has a higher edge over that. Okay. So that was about the leakage current suppression kind of a circuit. Then we have worked exhaustively on switched capacitor, common ground type structures. Now the idea here is, as I already told, the DC bus neutral point would be connected directly to the grid neutral. Okay. The moment we do this, one of the main challenge that comes in front of our eyes is that the capacitor, the switched capacitor, what you have should take care of the entire negative half cycle. Okay. So this switched capacitor, I mean, not in this case, in general, any common ground type structure that you see, the switched capacitor has to take care of the energy requirement of the load during the entire negative half cycle. The moment that happens, that means the capacitor has to hold energy for a longer time. The moment capacitor holds energy for a has to hold energy for a longer time, that means we need a bigger capacitor. Okay, right? Because that is going to, it has to hold the energy for a longer time. So that is one of the drawback, because from the reliability point of view, if you look, capacitor is one of the, or you can also say capacitor is the most vulnerable component in a power electronic circuit. Okay, then comes the devices. It is the most unreliable, reliable, you can say, or that is prone to, or the lifetime gets affected sooner compared to your semiconductor. So capacitor has a failure rate. The failure rate in capacitor is higher, and especially when you go for a bigger capacitor, it is much more, right? Now, in order to avoid that, what was proposed in this structure is, instead of going for one single switched capacitor, a bigger one, we can have two, right? And the switched capacitor that will be used in the negative part, that is what is written. A majority of CGT available require large voltage rated capacitor and thus stores higher energy and increased capacitor requirements. So what we did is, in the negative half cycle, whatever the capacitor that is used in the positive is also used in the negative. So that is the overall idea. So the structure was built such that the capacitor that is used in the positive half cycle is also used in the negative half cycle in addition to the switched capacitor. So that way, the switched capacitor got a supporting hand by another capacitor, and the energy would be half, right? So the energy would be half, because without this structure, this capacitor, what you see, assume if it were to sustain a voltage of 100, now with the help of this, since we are going to add this to this, now it has to be only 50. So half CV square, the energy would be exactly reduced by 50%. So that is going to improve the overall power density of our inverter. So that was the main focus of this topology that was there. Okay. So this is the experimental setup that we had run. These are some of the key waveforms what you see, and this is the power loss analysis that we did with or comparison we did with respect to the literature. Okay, in literature there are several topology that were considered, and we run the thermal simulations. So from the thermal simulations, we saw these are the loss distribution that has happened. Okay, and this is the cost and volume analysis that we did. So this is a very exhaustive table which combines many things, like it combines the cost. Of course, it has a component count. Then the cost of your heatsink was also considered. Then the volume of the heatsink was evaluated. Then the heatsink cost was added to the inverter cost, which is switch, diode, and driver, and capacitor cost was added. So you can see in various at various levels, the inverter has been compared here. That is the capacitor cost point of view, capacitor volume, then inverter cost without heatsink, with heatsink, then overall inverter volume. In all regard, the proposed inverter has performed better, right? So even though you may see some numbers which are lesser than this, that those might not have a higher edge in the cost or something. There is always a trade-off, and these are the two functions that we generally use to evaluate, okay, to evaluate, and you can see that in this case there are few structure that are very nearer to the volume of the inverter, but they have their own disadvantage. So that is how we evaluate a benchmark our inverter in this regard. Okay. Now coming to the concluding part. So what are the challenges when it comes to a multi-level inverter that we specifically use for PV applications that are based on switched capacitors, right? Because this is one of the topic that is been researched heavily, right? Switched capacitor based inverters. Now, the key challenge that remains is the inrush current or the spike because of the capacitor, right? So this is one of the issue that has remained in the forefront, right? So it has to be addressed, and whether to go with the PWM way or whether structurally how are we going to address this issue, right? So recently there is a uh, movement towards the resonant based concepts where LNC are designed, the switched capacitor and the LR is designed such that it's a resonance happening. And then we can also have like ZVS or ZCS happening in our inverter. So that is where the movement is happening, right? So how to tackle this inrush current? Because this current, if it is of an acceptable level, then it is fine. Otherwise, it is going to severely degrade our capacitor lifetime, and also it is going to severely degrade our device lifetime because that current has to be sustained by any of the devices, right? So that is one of the challenges. Then comes the total standing voltage, that is your TSV and device stress. So this is what I was talking about, that the spike, the surge current would increase the current stress on the devices and the total standing voltage. Sometimes what happens in the process of building an inverter structure with reduced component, it may happen that some of the devices are going to experience a very large voltage or a blocking voltage across them. Right? So that is going to eventually increase their switching losses, and eventually it is going to increase the cost, right? Or if you have to have like a uniform devices, like you want to use a similar kind of device, then you have to go for a series connection of devices. So all those things have to be taken care. So that remains one of the structure has to be somehow designed that the standing voltage is not very large. Okay. Then we have capacitor size versus ripple trade-off. So this is what is the problem in CGT inverter especially, because if you go for a larger capacitor, then the ripple, if you want to keep the ripples in with acceptable range, then capacitor is going to increase. If that increases, again there is a loss that is going to increase. The size is going to increase. The density is going to reduce, right? So capacitor. So majorly the focus is on the capacitor part in case of a switched capacitor, because the structure, the rest of the structure, there is no much thing to be optimized there. Okay, it is only the part where we'll plug and play there, whereas the capacitor is the key focus. Okay. Now, what are the further exploration that we can look into is to go for GAN or SiC kind of devices, right? And soft charging topology. So this is what I was talking about. We can go for a resonant based topologies where capacitor would be soft charged instead of a large capacitor, large surge current, right? So we can go for a soft charging. Then we can go for a fault tolerant architecture, right? So that is possible. Even this CGT, what you see here, this has an ability to go for a fault tolerant operation. From 5 level, it can, if at all there is some fault, some portion can be isolated and it can sustain operation for 3 level. Okay. You can go for a 3 level arc. So a structure should be designed with some flexibility. So when you're building an inverter, it should have some flexibility, especially multi-level, that in the event of fault, like for an example, we have a switch or open circuit or a short circuit path, there should be some fault mechanism, the handling mechanism that should take care, and it has to reconfigure the structure so that if not 5 level, the inverter should at least go for a 3 level operation, or even in the worst case, go for a 2 level operation. That is your bipolar kind of operation. Okay. So those are more attractive, right? So instead of going for inverter, like there is a fault in one of the switch, the entire inverter comes to standstill, right? So that is not much appreciated, right? So fault tolerant, how to imbibe fault tolerance into our inverter, that can be looked upon. Okay. Then mission profile based analysis. So in this case, what is going to happen? Like even though we say that our inverter is designed for a PV system, rarely an analysis will be done by considering the actual PV generation data, right? So we take a PV, then what max we do? We are going to change the irradiation from 500 watts per meter square to 1000, or we'll change the temperature from 25 to 40 degrees. That all step changes, right? So that is what we test. Of course, step input is going to has a capacity to capture the transient response or the dynamic response of the system. But it will be better if you go for an actual PV generation data, right? Maybe a day, maybe a year or something like that. And then subject our inverter, whatever is or whatever is developed for that input, and see how exactly the inverter performance is there when we actually put out an inverter into a real world. Okay, so that is mission based profile. So with this, what is going to happen? The lifetime, that is another explanation that can be done, is the lifetime analysis of inverter, right? So the life cycle analysis you call, or lifetime analysis. So basically, we are trying to predict what is the mean time to failure. So when does, after how many hours of operation, our inverter is going to fail? That is one of the key area that many people are working. That we have built an inverter, right? So the PV panel life is like about 20-25 years, but our inverter lifetime is not that. Inverter would be like 10, max to max 10 to 15 years, right? So that is, and after 15 years, you have to either go for a repair or you have to go for a new inverter. So how to increase the lifetime? So when you say increase the lifetime, there the parameter that is going to majorly affect is the actual operating conditions. So that is where the mission profile comes into picture. When you subject inverter for real environmental values like temperature and irradiation, then we'll know what is happening or how does our inverter function. So keeping that in mind, then we can redo or reverse engineer and try to improve the lifetime of the inverter. Now, how to improve the lifetime of the inverter? Lifetime of the inverter is majorly decided by the thermal, right? The thermal aspects of the inverter, right? So even though sometimes the design might say that a 1%, 2% of efficiency is okay, means if you go for a lower efficiency, it is okay, but thermally the inverter should be sound. Okay, so you have devices, the inverter should be such that the devices have a thermal balancing that is happening, because even one of the device is thermally not feeling good, then it may get like it may, there could be a fault, and it is going to create a problem. Okay, so those are some of the areas that can be looked upon when we go for a inverted display. Okay, so these are some of the references that I have referred to, and thank you. So that's it from my side. I'll be happy to answer any of the queries.
Oh, thank you, sir. Any queries, please? If there is any query, please let us ask. You can type. So I think there is no query. Any query, please? You can type or ask. Well, so I think there is no query. So we are very thankful to Dr. Sandeep and from MNIT Jaipur for wonderfully discussing the various type of inverters. So with this note, thank you, sir.
Yeah, okay. So thank you the organizers for the opportunity. And if any queries, you can write to me. The mail ID is in the first slide, and you can also get it from the website. So that is what it is. So thank you. I hope there is some understanding that has come towards the multi-level inverters with this presentation, right? So thank you.
Thank you. Well, so thank you. With this note, we end our day 1 of our FDP. We will meet tomorrow 2 o'clock at the same platform with some other experts. So thank you very much. Thank you. And we have sent the Canvas email. So please register yourself on the Canvas where you will be getting all the recordings and quizzes, etc. and the study material wherever required. Thank you. संदीप सर आप डिस्कनेक्ट कर सकते हैं स्क्रीन
ये किससे कैसे कर रहा हूँ
थैंक यू